Thanks for everyone joining. It's great to see you all here, and I very appreciate your interest. So I'm going to talk about robotics today, exciting subject. And I start with giving you a little bit of background of myself. So I've been affiliated with lots of universities. So I started studying physics in Germany at two universities, the first two you see here. And then I spent a year at University of Utah, then came back to Germany, University of Heidelberg, finished my master's in physics, then went to Australia, University of Western Australia in Perth, went back to Germany to one of the Max Planck Institutes in Munich to do my PhD, while also working at LMU, one of the universities, big universities in Munich. And I did my PhD at another university in Germany, then went to the UK, do some research at the University of Edinburgh, which is one of the top computer science schools in the world. And then went to University of Southern California here in our neighborhood. And then since now more than 10 years, I'm with HRL Laboratories. I'm leading a research department at HRL. And so what I want to point out to you, so this has been quite diverse. I've been affiliated with 8 universities across 4 different countries. And on top of that, I'm married with a 5th country, with Taiwan. I encourage you in your career, seek experience in other countries, live in a foreign country, and try to go for diversity, particular diversity of mind, of thought, be exposed to many different cultures, many different ways of thinking. And in living in different countries, you get exposure to different ways of thinking. And also being exposed to different kind of fields is also very important. And what you will see here with robotics is a very diverse interdisciplinary field, which requires the close interplay of many different fields, and you can benefit by using different kind of knowledge from different fields, as you will see. So where's the state of robotics right now? And so it doesn't quite look like that. So this is not how the state of robotics looks like right now. This is the fantasy in movies. Where we are is, this is actually already almost 10 years old, but it is pretty much the state, or reflects the state. We are very good at fast pick and place. Pick and place works superbly, and we have perfectioned these things for automation, for manufacturing, for ordering, sorting, food industry. So pick and place works well. More recent, so this is what I've seen this year at the big Automation Expo in Anaheim, California. This year in February, so shortly before the pandemic broke out. So you can see what's currently right now there, what is available actually for purchase. You have robot arms that are on mobile units. They can drive around, for example, in a factory floor. You have small robots. They're very precise. They can do very precise pick and place. And then they can also take into account like visual input to pick up something. And we have sophisticated hand effectors like this robot hand. Those kind of hands, right now still more for research. Typically what you have in automation are this kind of hand effectors, like you see in this video, like a small suction cup to pick up something, or a conventional gripper. It's just like a linear gripper that opens and closes. This is still the standard for many things. And this is one area which is still very tricky. The flexibility of the human hand, we still, like in this robot hand, we still don't really have to the point where it's like really very reliable and very at a sufficiently low cost for manufacturing. So what we do in practice, we specially design end effectors, hands, grippers for a very specific purpose. Like for example, this needle-like end effector for picking up these tiny spheres on here. And then also right now what's happening, so NASA built, you've probably seen these fantastic large rovers and which are sent to Mars. So currently there's one right now on the way to Mars. It's about halfway to Mars. It launched earlier this year. And I've seen it being packed up. So that's the image on the right. It's at JPL in February this year, February 6th or so, when it was packed up. So you see the vehicle, the rover is there. So these wheels, they seem tiny on the image. They're massive wheels. They're like truck wheels. So this is a very large rover. And so this is just got packaged up at JPL, and then the next day after that picture, it got shipped to Florida, where then was sitting for a while and then got launched in a rocket on the way to Mars. So it's right now on the way to Mars. Yeah, this is very exciting. So these kind of robots, so they can drive around, and they have a robot arm. On one hand, actually two kind of arms. One is this mast here, which can look around, take pictures of the environment. The other one is a robot arm with a tool head, various different tools, for example, to drill into the ground and to analyze the soil properties. Because the main question we're interested in is there life on Mars, or was there life on Mars, and how did it look like? That's very exciting, because there might have been a separate evolution of life on a different planet, separate from Earth. And so that's a lot to learn from there. That's why people are very excited about this. And yeah, so here for the robot on Mars is mostly teleoperated. That means there's a whole team in a control center at JPL in Pasadena, and they control through the computer, through keyboard commands, or maybe through joysticks. They control all the actions of the robot. And it's not autonomous. So the autonomy is very limited, right? You can tell the thing, I'll go to this point there and it'll drive there. But very limited autonomy. And the reason is there's no autonomy and I'll talk about it later, it's still a very hard challenge. So that's another example. So another example of the state where we are. So that's one example of what I worked at USC. That's one of the works I was involved in. So we created motion plans to execute for the robot. And another thing here was we could create these plans that are very flexible, that adapt to changes to the goal point. And the goal point is here, this green sphere on the table. So we could move it around. And it also would, so this is an example where the obstacle avoidance is turned off. But when you turn it on, it'll move around the obstacle. And next it shows some more examples of the robot avoiding the obstacle. So you see here how the robot moved backwards to avoid the obstacle, or upwards. And while at the same time, the movement plan guides it to this goal, like this green disk, and you see it'll adapt to the changes. The neat thing here, what we had, you probably noticed this movement was fairly natural, like humans would move. And there's a reason for that, because we demonstrated this movement with a human, and the robot imitates the movement while at the same time being flexible to adjust to changes to the endpoint. So that's the new movement planner here was something, it can imitate your movement, but at the same time, while it's executing the movement, it's flexible enough to adjust to different endpoints. And then, so this is more recent, about 3 years ago. Boston Dynamics is a robotics company, as the name said, in the Boston area. And they've done impressive work with fairly large robots, more on the mobility side, for example, 4-legged locomotion, or just two-leg locomotion, as you see here. Yeah, that's quite impressive what they did. And but there's one important trick. It doesn't work that reliably. So what you do is you keep the camera running all the time and keep repeating. Because sometimes it doesn't work, and sometimes it does work. So it's still they've done an impressive feat at just getting it to work, but then having it reliably work is still another question. So for humanoid robots, it's still very hard to get them reliable to work, and that's why you don't see a lot of them. So what is actually the cost of these systems? So yeah, I mentioned Boston Dynamics. They have another robot, Spot Mini, which is now more on the commercial grade side. So what you saw with the big humanoid robot, that's not commercial. You cannot buy it. It's just not reliable enough to sell, to put out there. But the Spot Mini, there has been a lot of engineering now over the last 10 years. So they got it to the point that it's fairly reliable, and it's like a little dog can run around. You can mount instruments on there, and you can imagine it can run around in a potentially hazardous environment, let's say in a nuclear plant that got damaged and there's radiation around. It could run around there and take pictures. Or generally you could use it to monitor a site. The thing could run around. It could go upstairs, downstairs, and they're now selling it for $75,000. Still, it's quite some amount. It's not cheap. Then on the other hand, you have these robotic manipulators, like this example here by a company called Universal Robots. This particular version is called the UR5. And they typically have a price like $30,000, and this is also the price range you find with many industry robots, industrial manipulators, like the manipulators you see that put together cars, that solder together the cars, that paint the cars. For each individual robot, you talk about 30,000. The larger ones will be more expensive, more like 50,000. Smaller ones that fit on the table, you can get down, let's say 15,000, 20,000. But that's about the price range, right? So it's not cheap. And because of that, it's sort of in the price range of a more higher priced car, new car. And for that reason, there's also a market for used robots. You can buy used robots like for 10,000. And some of those robots, especially for manufacturing, the manipulators, they can be used to move things or paint things. This is now pretty established technology-wise, and they do last a long time. They can last 10 years. While a research robot, still like the Atlas down there, from Boston Dynamics, it's not going to last 10 years. It's going to work well for the video, and then it requires some maintenance. Probably during the fall you saw, it required again some tweaking, some fixing. These are not at the point yet that they will last a long time. And also the development cost is quite substantial. I don't, for this particular case, I don't know the development cost, but I guess it's more than $5 million. So it's quite some effort, and it quite some funding sources to get some big robot going, and then even more to get it going to the point where it's commercially viable, where you can actually sell it. Like the Spot Mini you saw up there, you see up there, it cost more than 5 million to get it to the market for sure. Yeah, so this is just to give you an idea what the cost right now. And there is definitely, if you're interested in business, there's definitely a market for, if you're on the low very low end side, let's say we can have a robot for $5,000 that's really reliable. There will be big demand. And there will be a market for, I mentioned the end effectors. Still relatively expensive and still very much specialized. Specialization essentially means I have a new task. Let's say I want to insert something into something else. And I need to design a specific end effector for that. Just the design, the prototyping and iterations easily cost $100,000. And so having something that's more flexible that you can use for more different tasks, and having also something that's relatively low priced for the end effector, also there will be a market. For the next section, I want to talk about what does it actually take and what skills do you need to make robots work. So let's have a look at one example. This is manipulation. Manipulation means you have a robot arms, and it does something on a surface, maybe picking up something. Or one example could be you pick up products and you put it in boxes. It's something that actually happens if you, in distribution centers, you need to sort things, you need to store them away. And so one thing you need to have at first, you need to have what is called a perception system that is able to figure out based on visual inputs. This could be like cameras on the head of the robot, for example, like in this one here. And or other kind of depth sensors. There are sensors, you maybe have heard of LiDAR, that uses light in a way to scan a scene, right? There's a light, it shoots light, and light gets reflected on the surface, and I measure the time it takes for the light. So light seems to be very fast, but it's not infinite, has a finite speed. And we have clocks that are super accurate, so we can actually measure short distances, even like a few centimeters through the light, which is fascinating. So you can get, with this kind of LiDAR sensor, you can get a depth map of a scene. You can use stereo cameras like the humans use to create depth from two images. And so what you want to have, like in this scene here, this shows like a point cloud that has some depth information. You want to get the objects, you want to know where they are in the 3D scene. It's still not that easy to get, let's say, if you look at this particular scene here, to get what's called segment, right? To get the outline of this object without getting the table as well. How do we know where's the boundary between this object here and the table? It's not easy for a computer to figure out. And how do you figure out how to grasp this thing? So that has been active research in the last, particularly in the last 10 years, solving this problem. And it's still, there's been a lot of promising approaches. I also worked on some of that, but it's not yet at the point where it's like super reliable and so it's like a solved problem. For one reason is just the perception itself, recognizing objects. To us humans, it feels so simple, right? I have this cup, I know exactly this is a cup and these are the boundaries. For a machine vision system to figure out this is one object and nothing else is not easy. So this is one part. We want to figure out where are things in the scene, and then we can plan trajectories for the robot, which is illustrated in the figure in the center. And that is the work we did, for example, at USC. We figured out how to generate those motion trajectories, like these red lines here, in a way that go around obstacles. Here, the obstacles are the red dots. So imagine this is the goal here, and depending on my starting point, there will be, this is a trajectory around the obstacles. And these are automatically generated. And yeah, this is the purpose of a so-called planner, to automatically come up with some trajectory. And you want to do this in a way that while you execute the trajectory, so first you plan it, right, to make sure you can reach an object or you can move an object. But then you also want to make sure while you do it that you can avoid obstacles, like you've seen in one of the videos. And then at the end, once you have this trajectory for the robot to execute, you need some software that tells each of the so-called actuators, like motors in the system. There's a whole series of motors to make an arm work. You need to tell the motors how should they move, right? At what power and what speed in order to execute the trajectory. So this is called the control. So you go from perception, the vision, to moving trajectories, and then to actually the control. Control means I generate commands for the many motors in the system so that it follows the trajectory. And then let's have a look at another example, which is for autonomous off-road driving, which is a more complicated problem. So off-road driving, I imagine you have a vehicle like on the right, and it's driving around some desert area or some rocky area. And then how do you avoid obstacles, right? How do you go around bushes? It again involves a perception piece at the beginning. And again, it involves getting some estimate of the depth of the scene. I want to get a nice, locally, a 3D landscape around the vehicle through my depth sensors. And then I can plan movements in this environment. But I also need perception, here the second box, perception that can tell me, oh, is this like surface muddy? Do I get stuck there? Is this grass? Is this a rock I need to drive around? Is this gravel very slippery? Those kind of things you need to somehow figure out from the perception system through some computer vision processes. And then again, when we figure out the terrain, when we know where are the safe spots to drive to, where are the spots to avoid, it boils down to a planning problem. How do I navigate in this environment, right? So then what you do is you plan many possible ways to drive through the environment. And then you, in simulation, sort of in the robot's mind, in the computer simulation, you evaluate which are the good trajectories among these. And then you choose the good one, and then you drive this way. But then as soon as you drive, maybe you see, oh, there's another rock. So you need to replan. This is a constant loop. You get your images from the cameras. You try to figure out what's in the environment. You try to plan, how do I go around the obstacle? You send commands to the wheels. And then again, take new pictures. Evaluate what's in the scene, right? Do you see mud? Do I need to stop? Do I see a big crack, a ditch in the ground? And so this is a constant loop, right? So people talk about like feedback loops, and people talk about control loops to make this work. And so I want to talk about more specifically in terms of, since you're now in the stage, right? You need to decide what you want to study, what to focus on. I want to tell you the kind of key ingredients that are very valuable, that form a basis to work in this area. And the number one is math. You cannot get around to some level of math in this area. And the most important tool here is linear algebra. And I guess many of you are probably familiar with matrix multiplication. You have like here illustrated here, you have a matrix times some vector, which means this vector gets somehow transformed into some space. Like, let's say, for example, imagine this projection, right? You have a point here in space, and I want to project it onto this, let's say, this camera image. This is called a projection, right? Because you have a camera centered at this location, and all the points in 3D get projected onto this image. The kind of math involved here is essentially matrix multiplications. Is all the field of linear algebra. Also, if you look at the whole robot arm itself, it's all a sequence of like little blocks that are shifted in space and then linked together. And in order to compute based on a certain angle of the whole sequence of chains of blocks, what is the position of the end effector? What is the position of the end of the robot arm, right? The gripper. Based on all the angles, this whole sequence of links, to compute this is essentially also linear algebra. You go through a sequence of matrix multiplications. and it can be written as a simple sequence of matrix multiplications. So this is a very key tool, and if you work in the field, that sort of always comes up over and over again in many different forms. And so it's being very strong in this area is very important practically, to be very comfortable in linear algebra. Then secondly, mechanical engineering is obviously very key. Though I want to mention here, not everyone in the field, I say these key ingredients, but not everyone in the field is an expert in everything, right? It doesn't need to. Some are more specialized on the math side, some more specialized on other things you will see, and some are more specialized on the mechanical engineering. Mechanical engineering is, for example, let's say you design a new end effector, and the way it's done these days, you use computer-aided design, 3D design. They're wonderful tools right now out there. I wish they would have been available 20 years ago, but these days are very have a lot of detail. You can design it on the computer, and all the detail is to see here in this example. You can make it move on the computer, so you can see how it will function. You can put together with other elements, so you see, is there any collisions, does everything fit together? And you can do some analysis, like for example, simulated stress testing, which involves some computer modeling that tells you this part here, there's a very high, so usually if it's a reddish color here, or a yellowish color, there's more stress at this point. In blue, there's no stress. And so this is very helpful to figure out if it could break, which otherwise you cannot see from just the simulation. So yeah, these are very nice tools. So and also on the mechanical engineering side, it's very useful to have some artistic talents, because it involves there's also aesthetics to it, right? Designing a new robot, you want to make it pretty. So artistic talents are also very valuable here. Then another key ingredient, computer programming. So programming is of course very key, and it's the whole brain of what makes robots work. It's on one hand we have the mechanical design, and then the building the thing, but then we need some smarts to get the whole thing to work, and it's all done in programming, which involves dealing with, how do I deal with sensor input, right? The camera input, how do I process it? How do I send commands to the motors? How do I deal with all the communications with the different sensors and everything? Everything is done in computer programming. And for robots, for my impression, the most popular language is C++, because it's more closer to the machine level. And also, if you compare it with other languages, you probably heard of at least some of you know about Python. C++ code is directly converted into machine code, and therefore closer to the kind of things the machine can handle and faster than Python code. So yeah, if you're into robots, so I think there's no way around C++, and C++ has been around for more than 20 years. Actually, yeah, it's much older, but in this area at least, it's been used in robots for at least 20 years, and so it hasn't really changed, right? Despite the many changes and despite new invented programming languages, people still use C++. So I expect it to be still valuable in the future. Then another key area is computer vision. Computer vision involves taking images from a camera, and then when you take images from a camera, they then get stored. You get them on the computer, and on the computer they're stored like a matrix. It's like, imagine a two-dimensional array, and so it's an array of pixels, two-dimensional array of pixels. Imagine like a chessboard, right, kind of array. And then for each of those pixels, you have the color information. And computer vision deals with processing these arrays of pixels. And one of the simplest way to process is getting the edges, like in this example. You can, and this can be done in an automatic way. You can essentially you look at the contrast, right, of two different colors. And then to compute edges, edge detection has been a very long history. Yeah, 50 years or more. And so there's been a lot of done. It's kind of, I guess, saturated. I expect not too much more, but even despite the 50-year history, there's been algorithms like that within the last 10 years make some improvement. It's fairly established field, getting edges from pictures. But then you want to do more things, right? You want to locate where things are in an image. You want to locate or maybe identify also what's in the image, right? Do I see a car in the image and so on? And this brings computer vision very close to a more popular area these days is machine learning. And I went to the #1 computer vision conference over the last 3 years or so, and their computer vision machine learning is like one thing. These days, computer vision is all about machine learning, because what you do is you take tons of data in machine learning, let's say millions of images, and you have, let's say you have labels for those images. So you have images of cars, images of pedestrian, images of bicycles, and you have millions of those, right? Each with a label, tell you which is which. And then you use the machine learning algorithms to predict what is the thing in the image, right? I predict this is a car. I give an image from a car and I predict it's a car. Or I give an image from a bicycle, I want to predict it's a bicycle. Or as in this image example, I want to not only predict what it is, I want to predict where is it, right? This is called object detection. Where in the scene is something? And I want to detect all the cars where they are. And this is obviously very interesting for autonomous driving, but also for, let's say, city management. I want to know how many cars go through that intersection. There's been a lot of talk about like so-called smart cities. And that's one way what they do, right? They monitor traffic, pedestrian, cars, just to see how much goes through a certain interaction. How can we improve traffic flow? And so this is a big area, machine learning and computer vision. And then the robot problem is often very much boils down to perception, computer vision. The robot needs to know what is in the scene around it, because it needs to grasp something. It needs to avoid an obstacle. For that, it needs to know where everything is. And often, at least these days with our knowledge, once we know where everything is, it's a relatively easy problem for the robot. But knowing your environment, the so-called situational awareness, is still very difficult. And a lot of research goes in this area right now. And then another important area is biology and cognitive science. And we can learn a lot from biology. For example, looking at real cheetahs, and they're amazingly fast, right? They can go 70 miles an hour just for a short time, but still peak speed very fast. Could outrun any human. And also extremely high acceleration. It rivals a sports car acceleration up to 0 to 70 miles an hour. And so they're amazing, right? So we can learn a lot from what is the mechanics, how do they keep balance? How do they manage to go so fast? Which is of interest for robots if you're interested in leg locomotion. And I also worked on some of that aspect. So how can we learn? What can we learn from the fastest land animal, the cheetah, in terms of leg locomotion? So there's still, in the past, there has been a lot of leverage from biology, but there's still opportunities learning from biology. And another thing is obviously the brain, especially the human brain. Since we have this amazing capability, And then there's obviously a lot to learn, but this is a very challenging area, but because we understand still so little about the human brain. There's been a lot of progress in the last 10 years understanding the brain, but still it's very challenging. We still don't fully understand it. So this is very interesting research-wise. And then while we can leverage our understanding from the brain, for example, to create better methods for machine learning to understand the environment, at the same time, this interdisciplinary effort, trying to understand the brain, trying to improve machine learning, the whole loop of the two, and in this joint effort, eventually also improves our understanding of the brain. So it goes both ways. By trying to build something, we can understand it better. And there's a famous quote by the physicist Richard Feynman. He was at Caltech, and one of the things he had on his board was, I do not understand what I cannot create. And yeah, that holds true for many things, right? Especially if we look at biology, the human brain. As long as we don't know how to build it, we don't really understand it. Then, yeah, finally, the last two important points here is, so to make robots work, it's a lot of testing. You just need to test over and over again. And you also need to test the real world, because while simulations get very, very better, we can test some of the aspect in simulation. Like I showed you before with this stress test simulation, some things we can do in simulation, but at the end, it's so complex, so many different parts, and the interaction with the environment, bumping into things, and the real world vision and everything is so hard to simulate. So at the end, it boils down still to this state. There's no way around a lot of testing with a robot. So you do it over and over again and try to improve it. So that's a big time effort. It's very important. And finally, teamwork, since this is an interdisciplinary effort. You've seen it involves mathematics, it involves biology, it involves mechanical engineering, computer vision, machine learning, and all those fields together. Rarely anyone has expertise in all of them. So it requires good teamwork, which means it's one very important skill is good communication, being able to communicate the vision and being able to facilitate communication within the team to make something work. So communication is key, and teamwork is key for making robots work. Also, one thing I also want to mention is, so there's sort of two ways to go about it if you want to work in this field. You can be an expert in one specific discipline, let's say mechanical engineering, and then know everything about it. That's very valuable. Or as an alternative, you can be very broad, have expertise in all those areas I mentioned. Then you won't get into the same level of detail. That's not possible. But you have a broader language, a broader knowledge of all these areas. And both of these capabilities are important. We need people that have the overview of everything, and we have people that have the special knowledge, and all can work together in the team. So to summarize the key ingredients, we need mathematics, right? It's just the basic, right? So sometimes in school, if I see, and I had the same experience myself, right? If you see the school homework and the problems, they don't feel very much related to real world problems. But working in this field, there's so much need for like linear algebra and this kind of metrics, vector multiplication and manipulation. It's very valuable. So it's good to have a good background in that. Then mechanical engineering, right? We need computer programming is key. Everything is software, right? And if you're good in software, you have a lot of opportunities because it's not restricted to robots, right? Everything these days, a lot of the things is based on algorithms and software. And then in particular, like computer vision, machine learning are key here. Then biology, cognitive science are great for learning, for getting new ideas. And then finally, lots of testing and teamwork. So this the key ingredients to make robots work. So now we're almost at the end. So where are we going from here? So how does the future look like for robots? And looking at the movies or Hollywood, it seems like we have humanoid war machines have been very popular. Humanoid household helpers. By the way, this is the one in the center. You may not know because it's a very old TV series in the 60s called The Jetsons, and there was one robot, Rosie. It was very, very famous. It's a household robot. And then finally, human-like intelligence and emotions. All this have been very popular, and interestingly, almost always in some humanoid form or with some very human-like qualities. But that's not really how the future, at least in the next 10 years of robots, look like. So it will be none of these, and they have been in the movies for 100 years. I think the early movies, probably 100 years ago, they already had some visions of robots along that line, but it's still not in our life, and it's not going to be in the next 10 years. But so what will be instead in our life over what do we expect over the next 10 years? One thing is fully autonomous driving might be a possibility. It's still, I put a question mark there, because that's one of those areas where people starting already, at least in the 60s, I've seen a commercial in the 60s from a car company that predicted an autonomous driving world in about 10 years ahead at the time, in the 70s. It didn't come to pass, obviously. And in the 80s, right, I know colleagues who thought in the 80s, we have autonomous drivings just within the next years, still didn't happen. There have been these predictions for the last 50 plus years that autonomous driving is just about to happen. It never happened. But the last 5 years has been a little bit different. There's been a lot more investment. All major car companies have a huge autonomous driving effort, big investment. And with the machine learning progress we saw in the last years, with the computer vision progress we saw in the last years, it seemed to be a lot more likely to happen. And we've seen at least demonstrations that a car can drive 50 miles or so without touching the wheel, or almost never touching the wheel. It can navigate traffic, can drive pretty well, probably better than many humans, but it's not quite at the point yet it can function in all situations. There are always some what we call corner cases. There's always some special case, sort of out of the extraordinary, that we humans with our intellect, we sort of can reason about it. But then for the machine, it's totally lost. And one challenge is with autonomous driving is you cannot just say, if the machine doesn't know what to do, oh, I give up, take over. Because at that moment as a driver, and you probably experience that later, right? It takes a moment to just get into the scene, right? To get into this job of driving. You cannot suddenly switch from reading a news article like here to driving, right? You will be shocked, right? If this car suddenly says, oh, I don't know what to do, take over. And then you first figure out, oh, where I am, what is in front of me? And everything happens at high speed. That's why this is a big challenge. So it's one of the things that it might be possible within the next 10 years, but there's still a question mark. But I'll tell you other things that I think will happen. One thing is we'll see fully autonomous warehouses. And these are warehouses, for example, for distribution centers. Amazon, as one example, has a lot of distribution centers where they collect all the items and then package them and then ship them out. There's a lot of automation already happening. For example, they have robots to move around bins. They have robots to pack packages. But there's still here and there's a human in the loop, and it's not fully autonomous. And that's something what has been identified in the industry as a sort of low-hanging fruit in quotation marks is something that's it is doable. It's not there yet, but it is doable, and it is doable because it's a more controlled environment. I have my warehouse. I can control the lighting. I can control the robots in there, and I can control the items I'm working with. And most of the time, I'm working with boxes, which have a nice, very controlled shape. And so geometrically and visually, it's much more controlled. And for that reason, it's I think something that will happen. We'll have fully autonomous warehouses, not just one, which is now we have partially autonomous warehouses. We will get fully ones, and essentially they can operate on their own and for delivering stuff and online delivery. Then we'll have more automation in manufacturing. There's already automation in manufacturing, for example, in the car industry. Welding together the aluminum plates into a whole car body is done by robots. Painting the shell of the car is done by robots. But then we still have a lot of humans that put in the different components into the car. And so we will see more automation also in this area, that more and more of these individual jobs will be done by robots. It will first start with things that are very structured, right? Manipulating things that are more rigid. Manipulating like soft tissue is still very hard. And it's sort of, we know how to pick up something that's soft, but then placing it in a location that we exactly know where it's supposed to be. Let's say it's like part of a seat, and placing the soft cover in a way that it's really in the right location. It's still very hard, but we'll see more effort along this line. And also one of my projects, I'm working on automation in manufacturing to make something autonomous or make it work in an automated way that's still done by humans, manual labor right now. And there is, well, there's been a concern, right? Robots taking over some jobs, but there is on one hand, it doesn't happen quickly. On the other hand, there's always a gradual shift, right, of kind of work that we do as humans, right? We don't do the same kind of work people did 100 years ago, and some of the things involve like shoveling coals or dealing with big steam engines, and for the most part, we're pretty happy that we don't need to do this work, because a lot of that work was pretty dangerous, and accidents also have gone down, work-related accidents, and so we will see sort of we're part of this trend, and it'll just continue that things now, and maybe now we feel like, oh, it's maybe not that nice that this particular job is being automated, but then 10, 20 years from now, we are happy about it, and that the people are happy that they do different kind of work. There's always different kind of work, and it's more a matter of creativity. It's also the task for the entrepreneurs and the creative people to come up with new things that people can work on. And it'll always change as part of the change. And then finally, the last area is, I think we'll see a lot more robots in the food service industry. And this is, let's say, for serving a cup of coffee, for preparing the food, especially, I think, fast food and the kind of things that are relatively low price, like a cup of coffee. We'll see a lot more automation there. And it has certain benefits. For example, imagine an example of coffee. You already figured out how you want to have your perfect coffee. What is the exact amount of powder and so on is in there, and it's sort of stored in your app, or it's stored in the cloud with your favorite coffee company, and then you just go there with your app, and then you just order it, and you don't need to do anything because it's already stored. And because it's automation by a robot, we can precisely control the amount of water, the amount of coffee powder, the amount of any liquid you want to add. It's perfectly customizable and controlled, and it can switch from one customer to the next immediately. And so those kind of things, I think we will see. And it's the areas where there's opportunity. In the fast food industry too, it's economically a challenging industry because of low cost. And that's something where the robots can deliver more customization, hopefully better quality fast food too. And yeah, so that was the end of my presentation. Thanks a lot for your attention, and feel free to ask me any questions.
Okay, it looks like I have one. Do you have any advice for students interested in science and engineering careers?
Right. Yeah, that's related to sort of the middle part of my talk, what I was presenting. So math is key, and it's a very crucial foundation, but it's not everything, right? Try to go towards, as I mentioned at the beginning, right? As one of your goals, have diversity of mind. Try to be exposed to many different fields in the area, right? Like biology, math, physics, chemistry, mechanical engineering, everything is valuable. And especially in the beginning, like let's say you go out to university, your first year at university freshman, I think at that point, it's a great idea and a great opportunity to do as many diverse classes as possible. Right? Try to expose yourself to many different ideas for two reasons, right? On one hand, you want to get a broad knowledge about what are the possible, you want to sort of get an idea how does everything work together, right? So you need to know many different things. On the other hand, at the beginning, you don't really know yet what you really are most passionate about, or what you really are best in, right? What works best for you. So from that perspective, it's also good to have a bit broad perspective. And then as I said, at some point, then you need to choose, right? You want to specialize in one area, or you want to get more broad. If you want to go more broad, that's valuable if you go more to the direction of entrepreneurship, right? Leadership roles, because then we need people who are more broad. If you're more interested in a very specific aspect, if that is more fun to you, then you focus on a very specific element, let's say mechanical engineering, and try to learn everything about it you can, because that's also very valuable.
Mm-hmm. Okay, I have another one. If you're able to share, what other projects are you working on right now? You talked a lot about the generalities of the robotics field, but what do you hope that what you're doing will lead to in the future?
Yes. So one thing I'm working in is in robotics and automation, pushing in areas that are still done manually. And I cannot tell you the details right now at this point, but at some point you will hear about it. And so we are looking at a process which humans have done in this particular case for more than 70 years, the same process. And now we're going to automate it with robots, and it will be completely autonomous, and it'll have with many benefits, right? We have fewer injuries. It will be done more reliably. And so then the hope is then the humans, instead of doing that work, they can supervise the robots and then doing some other things. So in terms of education, right? So it's having the right education is also key, right? Because you don't want to get into an area that's then it's going to be totally automated, because it is a dynamic world, right? We cannot assume a dynamic world. It is going to change if you like it or not. It is a dynamic world, and it will change. The skills will change. So you want to be adaptable, and you want to go towards something that's sort of driving the change. And it's more fun to be part of the effort to drive the change and to create new capabilities. That itself creates also jobs, right? There's a lot of jobs, and just making those robots to work, it's a lot of effort. Just on the programming side, right? We need lots of, and there's always, wherever I was, there was always a need for someone who's very good in coding. Never stops.
Okay, I think we can do one more. Are there a lot of new startups in the robotics industry? Because apparently it costs a lot of money to develop, and where do these people get their funding for these
Yeah,
projects?
that's a very good question. Right now I don't have the numbers. I didn't look up the numbers. There's a pretty good number of startups. Certainly, I think today probably a lot more than 15 years ago. But it is not an easy area to get started, exactly, because it is many things relatively cost. It costs a lot to get started, right? With $1 million, it's not much you can do as a starting budget. But there's ways around it. You could focus, for example, on and that's what people have done, right? Focus on an aspect of it, maybe the computer vision side, and which is a lot easier to get started. Actually, you can start with zero. You just need time. A lot of the tools are available for free, like all the machine learning tools, some of the, like there's a computer vision library called OpenCV. There's a lot of, like Python, right? There's a lot of free tools. Machine learning uses a lot of the Python programming language. There's a lot of tools out there, which is just free on the internet. And the only investment there needed is time. And so you can get something started. And if you create a capability, let's say in the computer vision space, in the machine learning space, that can be used as a part of a tool for a bigger robotics effort, that's also valuable. And some companies started this way.